So welcome back, guys. Today we start with the small problem on matrix completion. I'll take this is a problem one in the textbook in Professor Gilbert Strang, page 200. Okay, and from the Professor Gilbert Strang textbook. And here he's giving 3 matrices. And he wanted the same matrices we had in the lecture part. He wanted to complete these matrices using a different scheme, which is the minimization of what we call the nuclear norm. Okay, so they have 3 matrices. I'll start with the first one, A0. What is the nuclear norm, guys? So you have 1, 2, star, star. What is the nuclear norm, Firas? Yes?
The sum of singular values.
The sum of the squares of the singular values. Okay, so if you are completing it to A, should be 1, 2, let's say xy. Got it? Okay. Now, what is the nuclear norm of A? It is the sum of the squares of the singular values. Here, of course, we are aiming where we could say that the maximum rank of this matrix is how much is 2, right? Because it is a 2 by 2. In general, the nuclear norm is the sum of the squares of the singular values. Okay, so let us work on the singular values. To produce the singular value, we know the scheme, right? We know the methodology to follow. We have to find the eigenvalues of AAT or ATA, okay? And take the common part. Are you okay with this, guys? You still recall this? Okay, let me write it R instead of N here, okay? Should be R, okay? R here is for the rank. So let me compute the matrix AAT, first of all, and see what happens. Here, if you do the math, AAT would give you how much, guys? Let's do it together. So suppose you're placing AT here, A transpose. So you're doing 1, 2, XY multiplied by, here I get 1, 2, XY. Am I right? So for sure I get 5, there's 1 plus 2 squared, right? 1, here I get x plus 2y. Here again, x plus 2y. And x squared plus y squared. Are you okay with this, guys? Okay. Right? Now, to find the eigenvalues of this matrix, we need to find the solution to the determinant of, let's say, let's call this matrix, you're gonna wanna call it. Let's call it, instead of using B's and C's, let's call it big W, okay? Capital W. So determinant of W minus lambda I, how much is it? Is going to be the determinant of 5 minus lambda. Here I get x plus 2y, of course. Here I get again x plus 2y, and finally x squared plus, don't be scared, guys, because there is something simple that's going to happen. Minus lambda, okay? So of course, this is equal to, I did the computation, so it's going to be equal to, you can repeat it afterwards, minus lambda times x squared plus y squared plus 5. And minus, here the last part is going to be minus x plus 2 squared plus 5x squared plus y squared. 5y squared. You can just do it with me right now and check that. It's okay. So to solve the second degree equation, of course, this would be equal to 0 with respect to lambda. You will have to use the discriminant, and here you will set your delta, which is the small b squared minus 4ac. It would be equal to the following. It's x squared plus y squared plus 5 squared, of course, minus 4 times. If you do the math, there is some kind of arrangement you can get, and you get the following. And what else? Okay, I think you get something like this. Okay. Okay. It doesn't matter what you get after this. So let's say I'll have the two eigenvalues, lambda 1 and lambda 2, which could be written this way. It's going to be minus b, so x squared plus y squared plus 5. بعدين plus or minus square root of delta. Am I right? صح?
Yes.
Okay, divide by 2. So if you think of it now, if I go back to the nuclear norm now, if I'm summing up two consecutive eigenvalues, whether for an ascending order or decreasing order, the plus and the minus delta are going to disappear, right? So you end up with how much? You end up with just this part, x squared plus y squared plus 5. Got it? Yeah. So at the end of the day, if you're willing to match this, the solution is obvious. You need how much? You need just to get these two guys equal to 0. Okay? So the right way to do it then is just to say that A is equal to 1, 2, 0, 0. So at the beginning, the problem, looked like kind of complicated when you reach that part. But when you sum up these eigenvalues, which are in fact the squares of the singular values, you end up with a very, very easy problem. Okay? Got it, guys? In fact, even with the next matrix, in fact, in the problem, he's giving three matrices. So the second problem, the second part has this matrix 1, star, star, and 4. And he needs to complete it also by minimizing the nuclear norm. If you do the math also you will end up with the same result. In fact, you can do it. You end up with the nuclear norm of B. So let's say that I'll just give the couple of steps. So you need to write B, which is equal to how much? 1xy, let's say. 1xy and 4. And the nuclear norm I got is the following. You end up with the following. It's going to be equal to just x plus 1. Okay? So this is for, no, sorry, this is for the next one. This is for C. This guy should be, yeah. This is for C, sorry. This should be for x squared plus y squared plus 17. Okay? So this is what I got. And again, you will get these to 0. Okay? So you should place zeros there. The last question, which was the last matrix, has C0. And here the result is totally different because we're C carrying 1, 2, 3 star. You get just to put one item there. Let's say we call it X. And if you write the nuclear norm here of C, you find out that this guy should be equal to just x plus 1. So if you're willing to minimize here, if you have no condition on the x, here the problem is unbounded. So x should go to what? Should go to minus infinity. Okay? So unless you're assuming that x, the least value for it is 0, the problem would go to minus infinity. Unless x is larger than 0. Then the solution should be again 0. Okay? Got it, guys? So this is just an introduction to the problems you got there. Hopefully, we'll come back and the homework and do a couple of problems with matrix completion. Okay, guys, any question? That was problem 1, page 200 from the book.